So because there are more problems, so then the grades should appear a bit later than for the usual quiz. No, there was no extra problem for this midterm. I think we'll add it for the next one. I mean, for the quiz. Yeah. So we'll have 3 weeks left. But overall, the level of difficulty of the quiz, was it? What do you think? Was it about the same, or was it easier than the previous the midterm? Was it easier? Was it harder? Is it the same? Well, I mean, it didn't say so, right? So the okay, we'll see what you guys did. If you think if the last problem was too hard, we may exclude it from the mandatory credit. I didn't find it particularly hard, but yeah, we'll see what the score will be. I think maybe one of the students haven't taken the quiz yet, so we should be able to. So the midterm was a bit harder than the quizzes. Is it because of there were too many problems, or because each of the problems were a bit harder? A bit more difficult, huh? But again, because of individual problems or because of everything together? Those who think that it was harder. Okay. So as far as final goes, I think it will be pretty much midterm multiplied by 3 halves in terms of number of problems. So you should expect that, and maybe some one or 2 problems for extra credit. And I'm actually thinking maybe we should do the final, open book, take home 24-hour thing. So it will, but this way we can make problems harder. So we can probably take a vote or something. So because there were so many people who had problems with uploading their solutions in time, so I can either give more time, or we can just have much more time, right? So something like the whole day is yours or something like that. We'll see. So I know that some of you were pressed on time. Yeah. So far I'm thinking doing a unit for 4 hours, so the standard 3-hour final in class, and this is because it's take home to have it 4 hours. Okay, good. So let's move on. So we have a large, sort of vast topic today, this week as well. So this week we will be talking about integrals. In particular, we'll talk about double integrals and triple integrals, but most, and then of course any, we have many integrals, which of course nobody writes that many integrals in a paper unless they want to emphasize explicitly what are the limits of integration, right? And so on. So we can, we'll replace it just by some integral over some multi-dimensional volume or something like that. So our task today is to define, so today we will mostly be focused on double integrals, and we'll talk about what is a Riemann integral in general. So by integral, we imply Riemann integral. Do you know any other types of integration, any other integrals? So there's integral by Riemann, and there are several, but what's the next most famous one? What was the name of that person? Which spelling I'm about to check again, because it's not my strong side. So you probably heard of, yeah, so there's a Riemann integral in one dimension, like for functions, and then there's also this one, like I may mention later. So this is due to, that's how it's spelled, Lebesgy, and it's pronounced as Lebesgue integral. It is a different way to define integration over. So, in fact, let's do the review. And so we have, if we live in one 1D, if we live in one dimension, if it's a one-dimensional integral, then say you have a function f of x. X is between a and b, right? And then, so do you remember what are the conditions for such function to be integrable on AB? So we want to define a Riemann integral from a to b of f of x dx. So we'll talk about calculation in a second, but do you remember what was the requirement for this? Continuous, right? Either continuous or piecewise continuous. So we will allow some discontinuities at certain at certain points, right? So yeah, so it's defined here. So in particular, if f is continuous on this AB, then it will be integrable, and the integral with the procedure of integration that looks something like this, right? So you draw say there's a function, right? And then sequence A and B. So first we would introduce what is known as a partition P. Partition of segment AB, which works like this. So it's A is equal to T0, less or equal than T1, less or equal than Tn minus 1, less or equal than Tn, which is equal to B. So by partition, we mean the set of these ordered points on a segment AB. And the another measure, and then we also talk about mesh, or the size of the partition. Right, so mesh of the partition is the maximum difference, absolute value of the difference between the neighboring points. So in particular, we can take those points to be equidistant, right? So then mesh will be just b minus a. So if all are the same, if all intervals then mesh of P is equal to b minus a divided by n. And the, yeah. So we would do so this T1, T2, T3, and then there are several choices how to draw those rectangles, right? So one of them would be to, for example, pick a point in the middle, right? And then evaluate the function over here, and then draw the rectangle of the corresponding height, wherever this point might be. So I'm taking a middle point here. So this one is T2 plus T1 over 2. But we absolutely don't have to, right? So, and then we compose the sum. So f of value of the function of those points, ti plus 1 minus ti over 2, multiplied by well, it's always bigger than 0, but nevertheless, ti plus 1 minus ti, right? And then sum goes, so let's go with s subscript n, where summation goes from 0 to n minus 1, and because n is the last one. So yeah, so this is one of the Riemann sums, one of possible Riemann sums. When I say one impossible, I mean that we can also pick a point where we evaluate the function, not necessarily in the middle of those segments, but anywhere pretty much. So we can pick it an endpoint at the beginning, or we can do it, at some arbitrary point. We can throw a point randomly, or we can impose some conditions on that point, right? For example, depending on the nature of the function. So if you know for sure, let's say that the function is exhibits certain behavior in this interval, that we can adjust our calculation so that if you do it numerically, right, so when you calculate this integral on the computer, the algorithm will converge faster, right? By convergence, I mean that we want, and then, so in the end, the idea is that to take the limit as this Riemann sum goes to infinity, right? And if this limit exists, right, so then the answer is equal to the Riemann integral of f of x dx from a to b, right? So if the limit exists, then the function is integrable. If the limit does not exist, then the function is not Riemann integrable on this segment AB. So yeah, and then if you're interested in these numerical methods, then so people when they calculate actual integrals on the computer, they actually care about those things, right? Because that costs computer time. For example, and also sometimes you don't even have to do rectangles, right? So you can also do trapezoids. So for example, if you know that your function is growing like that, right, then of course it will be better. You'll be better off if you, instead of doing rectangles, which will definitely, it would be easier, of course, to do trapezoids in this case, right? Because even like to the extent that I'm drawing those this piecewise linear function, those sides of trapezoids, they almost precisely approximate the function. And then, of course, you just use the formula for the area of the trapezoid. I believe we used trapezoids earlier in the class when we talked about areas of rotational surfaces. So yeah, so that's Riemann integral of functions of one variable. So today we'll talk about 2, 3, or more variables. But before I go, I just wanted to ask: does anybody know what does Lebesgue integral do? How is it defined? So it's a new integral. It's a different type of integration, which is more natural to consider in some parts of math, like probability theory, measure theory. And instead of slicing the graph, like the area under the graph horizontally, vertically, excuse me, you would slice it horizontally. So what you would do instead, you would look at those kind of slices, right? And then you would compute your Lebesgue sum, or Lebesgue measure, so Lebesgue sum of this integral due to sort of by slicing it horizontally. So it may look like not much have changed, right? But in fact, sort of analysis is very broad, right? So you can, with a little bit of imagination, you can come up with an example of a function which is integrable in Lebesgue sense, but not integrable in Riemann sense, right? So you can have this. I thought I prepared the example for today, but yes, it's one of those. It's like, I think it's sine 1 over x times divided by x. But I'll confirm this after the break. Yeah, so I can give you the example. So there are functions that are Lebesgue integrable, but they're not Riemann integrable. Okay. Questions so far? Okay. Maybe I should make it a bit bigger. Now let's talk about 2D Riemann integral. Okay. So what the construction suggests is that we need to well, add another axis, right? So it's the integral over two variables, right? So we are given a function of what two variables, let's call them x and y. Let's call this z, so let's see, z is equal to f of x comma y. And then for the purposes of this definition, assume that x and y, they live in a rectangle R, which is just a direct product of intervals AB, closed intervals AB times CD. Okay, so just make it a bit more parallel. And now we will have a partition, right? So the idea is to introduce a partition of this rectangle. That's P of R by dissecting it into smaller rectangles, right? So if you wish, you can think of it as the product of two partitions, right? So it's a product of the partition of the interval AB and that of CD. So if partition of interval AB is equal to A, which is equal to T0, that's equal to T1, etc. Tn minus 1, which is equal to less or equal than Tn equals B, and partition of CD, C is equal to S0, less or equal than S1, etc. Sn minus 1, less or equal than Sn, is equal to D, this is B. Right, and then the product, right? So then we have the product of these two partitions will be a lattice of points on this rectangle R, So the vertices of the rectangle will have coordinates AC, BC, and this one will be, what is it? Something's wrong. Yes, AC, what was the other one? AB, right? Oh, no, that's right, yes, ACA, yes, AD. And this will be BD. Right, and this would be, so some point here will have coordinate TI, comma, SJ. Right, so this is a lattice spanned by, so the lattice which has intersection points TI and SJ. And actually, I make a slight, there's some imprecise formula here. M and N, of course, does not have to be the same. Right, so say there are N Nicholas, a number of intervals in X direction, and M Michael, number of intervals in the Y direction. So Y here ranges from 1 to N, J ranges from 1 to M. Okay. And then our task, and then of course, right, so it's analogously to, so we have two meshes. So but everything pretty much multiplies itself, right? So then we have mesh of this partition PAB, which is defined, well, as we did it, right? So then there is a mesh of partition CD. So you can define mesh of the partition P of R of this partition R is as the product of these meshes. Okay, let's write it down. So this is a maximum when it exists. So you may need to take the lower upper bound, right? It's the supremum, but let's for simplicity assume it's okay, right? So there's a maximum over all i's of Ti plus 1 minus Ti, and that is a maximum over all j Sj plus 1 minus Sj. So we just take the product of these two guys. Yeah. Okay. And now, so you can also denote the rectangle, subrectangle Rij to be the rectangle where the point Tisj belongs to the low left corner. Right. So this is the rectangle Rij. So now again we can pick a point. So in order to calculate the Riemann sum. Okay, so we pick a point on the rectangle. And again, sort of the choice of the point can be governed by your goals, right? So if you know what the function looks like, you can have certain idea of how to pick this point. But for now, let's assume this point is chosen somewhere, right? So so let's say there's a point, call it xij star, comma yij star. It's this point in this weird color. Yeah, it's a funny color. Yeah, and then we would evaluate the value of the function at the point, and then multiply it by the measure measure of the area of the of Rij, right? So let's draw a couple of. right? So we would pick this point, x star, y star, ij, ij, and say the function of two variables in this case looks like a surface, right? We know that, so it looks like some kind of surface. And then the image of the square, or rectangle rather, under the surface would look somehow like this. And that's the value of the function at this point, f of, oops, y star of ij. And now we are ready to set up the integration, the integral. So we have this. We can define the Riemann sum as Mn, right, which is equal to the double sum . Zero to n minus 1, j goes from 0 to m minus 1, f of xij star, yij star, multiplied by, well, the area of this Rij, which is ti plus 1 minus ti times sj plus 1 minus sj, which is of course the meaning of this formula is the area, right? It's the, you can call it delta a ij. It's the area of this rectangle. Right, so that's the Riemann sum. Right, and then the volume, excuse me, well, it will be the volume, but like if you have the limit, if the limit as well, actually the limit should be as mesh. Yeah, I think I forgot to say it in the first one, but let me say it here. So we take the limit when mesh of the partition R goes to 0, right? And then yes, in the sense that like the area of those small rectangles should go to 0. So if this limit exists, the limit of S and M, do you want to say here? Yeah, so like, right, so okay, let me just say here, right? So then the, right, so if this limit exists, then it is equal to the integral from A to B, integral from C to D, f of xy dx dy, right, in this order. So like the order of these integrals reflect to the order of differentials, or it's a double integral over this rectangle R of function f of xy. You can write it dA, or you can just write it, somewhat formally with two integrals, if you like, or with one integral, or just f, where you assume here that this symbol here is already contains the differential. So this is what is called a differential form. right? So either way, it's fine, right? So of course, when it boils down to the calculation, as we'll see soon, we need to take those integrals one by one, right? So you will take integral in x, and then you'll take integral in y. Any questions? So yes, of course, these things are all straightforward. Now, what is the meaning of this integral? Well, you have, we can easily figure this out. So if you draw the, so this, so clearly each of these terms here is a volume of a small parallelepiped, right, which is built on top of the rectangle Rij, right? So therefore, if you take the sum and then take the limit when m and n goes to infinity, right? So this also implies here that m and n go to infinity. Then right, so this integral here will have the meaning of the volume of the surface, or of the volume of the 3D solid beneath the surface. Or under the surface z equals f of x, y, where x, y, they belong to rectangle R. And that, of course, implies a certain, it only works if f of xy is greater or equal than 0, right? So only if the function is positively definite, then do we have this interpretation. Otherwise, well, the integral exists unless, or provided that the limit exists. But it doesn't have any interpretation in terms of volume anymore, because part of the graph that goes below the z equals 0 plane will contribute with a negative sign. Yes, it's important that this interpretation is connected to this fact. Right. Okay. Well, so let's look at some examples. So what do we do if it's negative? Oh, you just compute the integral. So it's the integral is, so like the interpretation in terms of volume is no longer there. That's it. Same true with the function of one variable, right? So it's the area under the graph if the function is positive, right? Sure. Okay, so let's take this a simple integral. Let's take, there's a function pick the rectangle R, which is, so x is between -1 and 1, and y is between -2 and 2, and the function, say here, it only depends on x. It's 1 minus x squared. Right. So if you draw it here, so you can see here that it makes a semicircle in x direction, right? So this is z, this is x. You have a semicircle from -1 to 1, and then from -2 to 2 is just it sort of stretches constantly, right? So it looks like a barn or something like that, right? So so that goes from -2 to 2. So so we see that this function is positive, So the integral, if you want to find the volume, right, it will be this double integral from -1 to 1 dx. Oh, not so fast, right? So from -1 to 1, from -2 to 2, square root of 1 minus x squared dx dy. Right? Now, how shall we do this? Manipulate with this calculation. So you see here, the function does not depend on y. So therefore, we should treat the integrand as a constant when we do the y integral. Right? So therefore, the y integral factorizes. So we can write it like this. It's integral from -2 to 2 dy, right? Because 1 minus x squared square root is a constant, right? And then we just can take it out. We can factor it out and then multiply it by the integral from -1 to 1 square root of 1 minus x squared dx. What is this integral equal to? You don't have to do it. You can just interpret it. So the integral from this function from -1 to 1 will be the area of this semicircle here. So it's a circle of radius 1. What is the integral from, what is the area of that semicircle? That's right. So r is equal to 1 in this case, so it's equal to pi half, right? And this integral is equal to 4, right? Because it's just 2 minus 2, so it's equal to 4 times pi over 2. So it's 2 pi. Okay. Now, we already see here that there's a certain choice that we need to make when we are doing a calculation of a double integral. Namely, which variable to integrate first, right? And then because there are two variables, there's a priori no, well, I mean, there's no rule that tells us which variable to choose. Rather, we'll choose this variable based on our convenience. So we can call this iterated integrals. So let me just explain by example. Say we have integral x to the function x to the 5, y to the 7, and then where x and y they belong to some rectangle R. So which is a let's pick the most generic one. So it's the one that we had in the derivation, right? And I want to integrate this function over R. How will we do that? Well, so we write this down: integral from a to b, integral from c to d, x to the 5, y to the 7, dx dy. And then, so let's first do the x integral, right? So if you do the x integral, it means that the y here plays the role of a constant, right? So therefore, we can write it like this. We can write it as integral. I'm going to swap them around here, and we'll talk about this in a minute. From c to d, parenthesis open, integral from a to b, and I put y to the 7 here, x to the 5 dx dy. So I do this integral. So y to the 7 stays, and here I get b to the 6 minus a to the 6 over 6, right? And then you do the dy integral. And then, of course, you get d to the 8 minus c to the 8, b to the 6 minus a to the 6 over, divided by what? By 48. So we have made the choice to integrate over x first. And that's why we call it iterated integrals, because it's one after the other. And then, of course, if you have more integrals, it's 3 or 4, or many, then you have to take them down one by one. Now, we could have made a different choice, right? We could have integrated them differently, right? So we could have done integral over y first, and then we would have done integral over x. And then, because, well, you can see here that the answer is symmetric, so the answer will be essentially the, I mean, it's not symmetric, but here it factorizes, right? So because the product, the integrand here is factorizable into product of two functions. One of them depends on x entirely, and the other one depends on y entirely, right? Then we can just do them independently. So in other words, we can write it as, here's integral from a to b x to the 5 dx multiplied by integral from c to d y to the 7 dy, right? And compute them like this. But you can probably understand that it does not always happen like this, right? So sometimes the integrand will be a function which is not factorizable into the product of functions, which so that one function only depends on x and the other function only depends on y. So we have to do integrals iteratively, one by one, in an order which will give us the most, which will be the most simplest to execute, right? So you would do the integral, basically, it comes with experience, but like sort of, you need to see which order to pick in order to get the answer in the quickest way. Okay, but so before we do some examples, let me give you the theorem. And of course, there are many examples in the homework, so I encourage you to start doing it right now. Well, after we're done. So here's the theorem due to Fubini, which says that if the function is integrable, right? So in other words, if f is, so remember, in the integrable functions are those which are continuous. So if f is continuous on rectangle R, right, which is the product of A, B, and C, D, then double integral over R of f is equal to integral over AB integral CD f of xy dx dy, and also equal to integral in different order. Dy dx. So if the function is integrable, if it's, for this example, if it's continuous, then we can integrate, we can do the iterated integral, we can integrate it in any order that we like, and the answers are equal. And then this condition of continuity, in fact, can be relinquished a little bit, so we can say that it's continuous everywhere except some number of points. We can allow discontinuity in a fixed number, in a finite number of points. But then we need to add boundness. We need to add that the function is bounded. Right? Because you can have a function which looks like 1 over xy, right? So that shoots off to infinity. So it's discontinuous only at that point, and the function is not integrable, right? So you have to impose boundness. Same, which is essentially the same condition as for the function of one variable. Okay, so also well, sometimes we'll adopt a notation with iterated integrals. So if you write integral like that, so which means here that we integrate over x first and y second. So you can write it like integral over from c to d dy. So that's the second iterated integral you will do. And then, but first you're going to do integral over x. Like that, right? So that's this guy here. And the other guy will be integral dx from a to b, integral from c to d, f of xy dy. So first you do the integral which is inside, well, internal integral, right? So that here you integrate over y and x is a parameter. The answer will be the difference between antiderivatives of function f, well, treated as a function of y, and it will depend on, well, this c and d, but also it will depend on x as a parameter, and then you will do the integral. Yeah, that's right. Questions? So we're not going to prove it here. The theorem is, the proof is quite tedious, but straightforward. If you want, you can ask me during office hours how to do it. So I think, given the time that we have, we should actually focus on calculations. Okay, let's look at some examples. Do it here for now. So let's take the function sine of xy multiplied by y over rectangle R, where R is given by product of interval 1, 2, and 0 to pi. Right, so see here, so clearly the function is not factorizable, right? So we have to pick the order of integration. So we need to come up with some order, right? And then do the integral. So which variable shall we integrate first, right? So if you integrate over x, and then we'll get some cosine function, right, with a sine, and then there'll be, we need to substitute. So it will be cosine of y, right, of cosine of things that only depends on y. Integration on y right away is not immediately obvious, right? So if you were to integrate over y, what would you do? What do you think? So say x is equal to 5, right? And then you're doing integral over y, of this function y times sine 5y. Remember how to do it? Okay, we'll get to that. So let's do integral first. We integrate over x first. So we leave out y from 0 to pi. And we integrate over x from 1 to 2. you can single out y here, sine x sine xy dy. Actually, let's not do that. Let's not do that. So what I'm going to do, I'm going to have to multiply sort of, sorry. Yeah, so functions like this, y times sine xy dx. Right, yeah, that's right. But like, so u sub, right? So u sub, but I thought with, so Han is giving the answer for, so that's the answer of antiderivative if you integrate over y, that's what we're saying? Yeah, I think so, right, sort of. Yeah, but like, my question was, how would you do it? What was the procedure? So would you differentiate over the parameter, or would you? Well, I mean, here you don't really need that. Yeah, I think, yeah. Anyhow, so thanks, Hannah, for the answer. So the iterated integrals to partial derivatives of functions of multiple variables, like integrals. No. It's like, well, I mean, in a sense, yeah. So it's a certain, well, it's like you integrate in this direction. Like you integrate in the direction where variable x changes, if you integrate over x, and then you integrate in the direction where variable y changes. And indeed, you can find in those functions where there are some problems, right? So these partial derivatives in different directions, they do not commute, right? So fxy is not equal to fyx. Then, as a rule of thumb, those functions will not be integrable like that, right? So there'll be some problem in evaluating, in taking those limits. Yeah, so you can think about it like that, right? So like roughly speaking, that's what goes on. It's like undoing partial derivative, so to say. So the antiderivative is integrated over y, right? So partial derivatives of that would be the function, and you got the idea, right? So there's no notion of the antiderivative, right? There are two functions, right? So one which comes after integration over x, and the other that comes after integration over y. But yeah, it's a very good question. Right. So now, well, the trick here, of course, would be to put y here inside the differential by parts. You want to integrate by parts. Yeah, I mean, you could, but here it's even easier. Like, in sense, the answers are already given. So when you put y here, right, you will have, let's write it again, dy, and then go from 1 to 2, sine xy dxy. And then you would, I think that's what you call u substitution or whatever, right? So that's integral from 0 to pi du dy multiplied by what? It's the integral for sine is minus cosine. That's minus cosine of 2y minus minus, which is plus cosine y. So because we integrate it over, like we substitute 2 instead of x and then 1 instead of x, right? Okay, and then that's equal to, so yeah, and then we just integrate, right? So it's minus 1/2 sine y from 0 to pi, and then plus sine y from 0 to pi. What is it equal to? Sine 2y, excuse me, 2y. Well, so I remember sine of any angle. So sine pi is 0, sine 0 is 0, sine 2 pi is 0. So every term in this formula is just 0. Was it clear how to, any questions, how we got from here to here, from here to here? So, yeah. Okay, so yeah, looks like there are no questions. Okay, let's do one more. Yeah, so we see here that the function is what? Well, the answer turned out to be 0. I'm confused by why the y went away. Well, y didn't go away, right? So it goes. So at this step, so this arrow here, we integrate it over x, or we can call it u, or whatever, right? So then the so integral of sine of something is minus cosine, right? Oh, it didn't, right. So I put it, so when we do integral over x, yeah, we move it inside the x, that's correct, yeah. So for the dx integral, it's a constant. And yeah, and that's how we do the integration. Good. Okay, so let's do one more example where we change the order of integrations. Let's say we integrate from 0 to 2 and from 1 to 2 function, which is x minus 3y squared dx dy. Right, so first we can do integral over y. So then we have integral dx from 0 to 2, integral from 1 to 2, three y squared dy, integral from 0 to 2 dx, and then here we have well, x, y between 1 and 2 minus y cubed, right? From 1 and 2. This is integral from 0 to 2 dx of x, right? So you have, well, that's just a 2x minus x, and then minus 8 plus 1. Okay, and that, so yeah, that's equal to x minus 7, which of course equals to x squared over 2 minus 7x, substitution from 0 to 2, which is what it's 4 halves minus 14, right, which is minus 12. So that's integral in one order. And in the opposite order, it would look like this. So first we integrate over x now. So we leave out the integral over y. And then integral in x looks like 0 to 2, x minus 3y squared dx. X squared half minus 3x y squared, substitution from 0 to 2. Four squared over 2 minus 6 y squared, it is going to be 4, not 4 squared, dy, which is equal to integral from 0 to 2 dy 2 minus 6 y squared, right, which is equal to 2y minus 2y cubed, substitution from 1 to 2, and that's 2 minus 16, sorry, 4, wrong again. It's 4 minus 16. No. Minus 2 plus 2, so that's minus 12. Yeah, so the answer is the same, although you can see that from the form of the expressions, the polynomials that were involved in each step, they look completely different. Right? Sort of that's the example that sort of shows it's the essence of the Fubini theorem. It's a polynomial function. It's nice and continuous on a rectangle, and integration does not, does not depend on the choice in which direction you do in which direction you go. Okay. Okay, one more definition from this chapter, from this section, is the average value. So by definition, if we have f, you can write it in this angle brackets, is let's recall what was the 1D definition of average value, right? So it was if you have an integral of the function f of x from a to b, right? Then the average was equal to 1 divided by b minus a, integral from a to b, f of x dx, right? So it was sort of the meaning of that was the kind of the, it's like, well, the value which is, if you replace it's the value of the function, so that the integral of this, of the area of the rectangle here with the height given by the average value would be equal to the given integral. And of course, it has a straightforward generalization to integral of two variables, to the function of two variables. Then of course you just divide by the area of the rectangle. So you're averaging over the function which is defined over the rectangle, and then you just do integral over here, right? So it has the same meaning. Okay. Any questions? Okay, let's take a small break, and I'll be back in a moment. Okay. Charlie is asking, how's everybody feeling about the midterm? I feel good about it. Yeah. So now let's see what happens if the set over which we're integrating is not a rectangle. So clearly, by construction, the rectangle is the easiest one. But now, what happens if we have, say, you want to integrate over a circle or ellipse or some shape which is given by certain functions on the plane? You know, before, I think I need to end up maybe 5 minutes prior. Okay, we'll see. So anyhow, it's integration over arbitrary regions. And that's 15.2 in the book. And arbitrary here means not a rectangle. So our goal is to define an integral over some region D of the function of two variables, where D is just a subset of R2. Right, so for example, D can be some closed region like that, right? So which includes the boundary. Or D can be a circle or an ellipse, or it can be bounded by graphs of some of two functions, right? So you have two functions, f of x and g of x, and we know that say these two graphs intersect at 2 points, say x1 and x2, right? And then in between, we know that all values here, these points are bounded between, so it's f. So we have several, I think we should pick a different name with f. Let's say call them g and h, since f was already taken. Now, so you have y is equal to g of h and y is equal to h of x, g of x and y is equal to h of x, right? And then we are plotting this set in the xy plane. And then we are studying a function f of x, y, right? So where x and y live in this set D, which is given by these two functions, right? So D is represented as such. It's the set of x and y in two-dimensional Euclidean space, such that x is between x1 and x2, and y is between, in this case, h of x and g of x. So this will be the more interesting example. We will talk a lot about this configuration and many problems in homework and tests will be of this kind. So we'll call this type of sets as belonging to type 1. It's when the set in the xy plane is bounded by graphs of two functions. And of course, it can be other way around. It can be not y is a function of x, so it can be x as a function of y. But let's say we have, right, so you can have, so that's one thing that's possible. Another configuration that is possible is if you have so again, I'm drawing the XY plane, right? And then f is goes in the third axis, right? So it's z is equal to f of xy. So it's some function that kind of lives on top of it, right? So the function is represented as a surface which is on top of that. Another example would be that you have, so like here, these two guys, I showed them as if they're intersecting, but they may not be intersecting, right? So you can have something like this, right? So you have one function here, you have another function there. And then one is greater than the other. Right, and that's your set D over which you're integrating. So this is set D. So this is y is equal to g of x. This one is y is equal to h of x. Yeah, and then the formula it's given by the same kind of formula, right? So you have as here, right? So it's you would describe this domain in similar terms. Okay. So our goal is to understand how to do this integration, right? Say let's start with this one. I think this we can call domain of type 2. But it doesn't really matter. You know? But the idea behind it is that, well, how can we write the integral over those domains if you only can integrate? Shouldn't use the word domain over the sets D. If you only can integrate so far over rectangles. Now, folks are already making some appointments. Yeah, I think I could enable you sending you private messages for more fun. Anyhow. And I thought in the age of Zoom, in the era of Zoom, it's hard to make new friends. Anyhow, so we know how to integrate over the rectangle. So let's make one, right? So let's embed this set D into some rectangle, which in turn is a subset of R2 in the following way. So say this is our domain D. Keep using the word domain. I'm sorry. It's set D. Domain is an open set, and let's consider these as closed sets. So there's a rectangle R, and D as a subset of R. Now, and the function f of xy is defined on this set D as it is, and then we'll continue it to the rest of the rectangle, so that trivially, right? So we write it like this. So we define function f of x on R containing D as follows. So f of x y is equal to, bracket opens, itself if x belongs to D, and 0 if x belongs to R but does not belong to D. So here the function is 0, 0, it's continued with 0. Now, the way the function is defined is discontinuous, but because it's bounded, so we knew that the function was integrable on D, So if D is closed, then the function was continuous, either continuous everywhere, or it could be discontinuous only at finite number of points, and it was bounded. So therefore, if we continue our function f to the rectangle in this way, it will remain bounded, and therefore it will still be integrable. And clearly, by construction, by definition, so this way we can define integral over d of f as an integral over r of f, where function f on r is defined in this way. Right, so simply because the function here is equal to 0, we don't really care, right? We just we can add that, like it does not change the value of the integral. And now we can just apply our methods of integration to evaluate this integral over here. Any questions? So in particular, we can, so what we did before, right? When we integrate over x first, we would integrate like this, right? Over strips over here. So we have a function bounded between here and here. And then you would integrate over y. Okay. So let's write example for type 1 and for type 2. I think I'm not going to use those types in my lectures, just to make connection with the book. It's up to every author. So let's take this example here, and so which is called type 2. And so we have the function which is defined on a set D, which is bounded by lines x equals a, x equals b, and y equals g of x, and y equals h of x. And let's find the integral. So this way, integral over d dx dy. So how are we going to do this? Well, so we will do the integration in y direction first, right? So it would go like that. And then we integrate over x. So we have integral over, so we do the x later in the end from a to b. And then we do integral from over y from h of x to g of x f of xy. Right? So see here, the opposite way may not be even possible, right? Because the function, so here, it's natural to kind of first to slice it vertically like this, because the graph is bounded by x equals a and x equals b. And when we integrate, so in a sense, you can sort of cut this set in terms of this vertical strips, and each vertical strip you can treat as a rectangle, right? So the value here of this point is x. The value of function here is approximately, right? So this is g of x, and here it's h of x. So we would integrate in y direction first, and then after we've done, we'll get a function of x only, which we can integrate over x. Yeah. So that's one thing. Okay, put it maybe in the frame, and then you can imagine what happens if you do it if the domain is oriented differently. So in another particular example, when the domain goes like this, okay, so we have And then there's a function x equals alpha of y and x equals beta of y. Here's the domain D. And then we need to do the opposite, right? So we would first integrate over x. So in this example, right below, the integral over y will stay the last. You integrate from alpha of y to beta of y dy f of xy. Okay. So yeah, the only new ingredient in this formula is the appearance of the variable in the limits of integration, of the limits of the inside integral. Let's do an example. Say domain D is given by the following. So we have graphs of two parabolae. So one is y is equal to x 2x squared, and the other one is y is equal to 1 plus x squared. So domain D is between, this is domain D. And we integrate the function x plus 2y. Right, so the function is linear. However, the domain is not a rectangular one. Okay, so first we need to find the intersection points in order to understand in which limits we're integrating, and we need to discuss which order we're going to do the integrals. Right, so clearly it's more convenient to do it like this. So we first integrate over the y variable, and then we therefore thereby integrating along those small rectangles, the vertical strips, and then we would integrate from over the entire x strip over here. Right, because we could have, if you attempt to do the opposite, we would encounter some problems, right? So say we can integrate like this. So like there's a strip that fits horizontally, but there's no strip that fits here, right? You would have to break it into pieces, and we need to know where the parabola breaks. So that's really complicated. Instead, we will do what I said in the first place. First integrating over the y variable. So let's start off by finding the intersection points. So these are the solutions of equation 2x squared is equal to 1 plus x squared. So x squared is equal to 1, or x is equal to plus and minus 1. Therefore, this point is minus 1, this point is 1. Therefore, the integral will go like this. So from the 2x squared here goes below, and then 1 plus x squared goes above. Of this function of x plus 2y dy. I'm going to continue here, the integration. Integral from -1 to 1 dx. And then integral over y of xy plus y squared. And a substitution between 2x squared and 1 plus x squared. Integral from -1 to 1 dx. So we're substituting for y, remember. X times 1 plus x squared minus 2x squared plus 1 plus x squared squared minus 4x to the 4. So there will be some polynomial here which we need to integrate. Yeah, so this is the function, like the it's the question is to find to integrate this function. That's f of xy. Right. So what we were talking before was just the general theory. How would we do the integration for any function f, x, and y if it's integrable? And here we're just looking at a particular example. So it's a linear function, f of xy equals x plus 2y. You know, it's some plane in 3 dimensions. And we are finding the volume underneath this plane, which lies on top of this wedge between 2 parabolae. Okay. So yeah, that gives us dx. That's minus x squared, right? So it's the x minus x cubed, and here we have what? 1 plus 2x squared minus plus x to the 4th minus 4x to the 4th. That's minus 3 plus 1 plus 2x squared minus 3x to the 4th. Yeah, and then we just do the integral. So that's what? That's x squared over 2 minus x to the 4th over 4 plus x plus 2/3 x cubed minus 3/5 between -1 and 1. And then, yeah, so some of the functions will disappear. Some of the integrals will be trivial, right? Because, namely for the integrals for odd functions, or rather, since it's a symmetric interval, integrals of odd functions will disappear. So therefore, here in the substitution, the even guys will disappear. So we don't need this, we don't need this, and the rest we need to calculate. So it's 2. And otherwise the answer will be doubled, right? So plus 2 times 2/3 minus 2 times 3/5. How much is that? So the common denominator is 15, right? And then we have this overall factor 2, which we can pull out. Two times 15 plus another, so here goes 5 plus 10 minus 9. How much is that? It's 25 minus 9. 16 times 2, 32. 32 over 15. Yeah. Here's the answer. Yes, as you can imagine, when the functions become more complicated, calculations will become more cumbersome, and it's very easy to make a mistake. So you have to watch your watch for those. Okay. Okay, now let's do a different integration in different direction. So another example. So now D is defined like this. So it's bounded by a line. Which goes this way, and by parabola goes that way. And it's the intersection. So parabola is given by equation x equals 1/2 y squared minus 3. And the line here is x equals to y plus 1. And here, right, so of course, in this example, and so the domain D is hidden between them. Right, so that's D. And so you want to integrate over D function xy. Right. So in this case, it will be easier to integrate in different direction, right? So we need to find intersection points here and here, which is what? So we need to solve this equation. So this is the intersection points. We'll solve 1/2 y squared minus 3 equals to y plus 1. Or it's y squared is minus 6. What is it? Sorry, yes, minus squared y minus 2y. This is minus 4 minus 8, right, is equal to 0. So therefore, yeah, so y is equal to minus 2 and 4. Right, so we have, yes, that's right. It's minus 2 and 4. So therefore, the integral would do as such. First, we integrate over x, and then integral over y will stay. And then here, integral of x will go from the parabola first, right? Because parabola is on the left from y plus 1. No, it's not the parabola. So yeah, so y squared over 2 minus 3, that's parabola to the linear function y plus 1 x times y dx. Okay, so the integral is rather straightforward. It's dy of x squared y over 2, and substitution for x between y squared over 2 minus 3 and y plus 1. So you can take out the 1/2. Then here we get y times y squared plus 1 y plus 1 squared minus y squared minus 3 squared. Okay, and then you need to do a lot of well, not a lot of, but there's some calculation involved, which will lead to, so unfortunately I have to run, I'm in a different location, so let me finish with this example. So it will be minus y to the 5th over 4 plus 4y cubed plus 2y squared minus 8y dy, right? And then after the dust settles, right? So it's equal to 1/2, and then we'll just do the integration, right? So it's minus y to the 6 over 24 plus y to the 4 plus 2/3 y cubed minus 4y squared. Substitution from minus 2 to 4, right? And then if you do the calculation, it will be equal to 36. So yeah, it's an example of a different type when you need to integrate from over x first and then integrate over y. So every time you need to be creative with the choice of the method. So some of them are better than the others. So in here, you could have done the opposite. You could have integrated along the x first, but then you need to split your integral into 2, right? Because everything to the left of this point, so here you could have done something like this, right? So you can find the integral over here of this part of the set D, and then done the other one. But you can see that clearly that makes no much sense, provided that there is a more efficient way to do it. Okay. Yeah, so I encourage you to start practicing ASAP. There are some examples in the homework. Yes. Do we need to graph it to determine which order we use? No, I mean, sometimes it's self-evident, but I think most of the time it's not really clear, right? So say I give you these two functions, this parabola and the line. It may not be easy to visualize that, you know, without plotting it. Like I won't require it for the solution, but I recommend it to do because it makes your life easier. Any other questions? Okay, so next time we'll look at more examples and do the integrals in polar coordinates. And then we'll talk about other stuff as well as triple integrals. Great. See you guys tomorrow. Thanks. Bye.